In today's lesson, we will be applying the fundamental theorem of algebra. So the fundamental theorem of algebra states if f of x is a polynomial of degree n where n is greater than 0, the equation f of x equals 0 has at least one solution in the set of complex numbers. In other words, if you have a degree of 0, you'll have at least one solution that could be either real or imaginary. There's a corollary to that, which simply states that if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided that each solution repeated twice is counted as two solutions, each solution repeated 3 times is counted as a 3, and so on. So basically what the corollary is saying is whatever your degree of your polynomial is going to that degree is going to be the same as the number of solutions you have. So if you have the 5th degree, you'll have 5 solutions. So let's look at an example. So we're going to identify how many zeros are in this function f of x equals x to the 5th minus 4x to the 4th plus 4x cubed plus 10x squared minus 13x minus 14. And the total, the number of zeros is going to be the same as the degree. So as I can see that this is a 5th degree polynomial, then the total number of zeros is going to equal 5. Now, if I were to, let's say, graph this, I could see that it looks like it only crosses the x-axis twice. So yet, how could there be 5 zeros if I only see that it's crossing, twice? But what I want to point out here is that here we have a local maximum that's just touching the x-axis at -1 and 0. This is known as a double root. And a double root counts as 2 zeros. So, in fact, this is showing two zeros here and 1 0 here for a total of 3 real zeros. So we're going to have 3 real zeros, but the total number of zeros we're supposed to have is 5. So that means we're going to have 2 zeros that must be imaginary, that we can't see on, that we cannot see on this plane, because this is the real number system. So making for a total of 5. So that's how we could read something. So we have to be careful. We have to be aware of these double roots, and sometimes we get triple roots. But mainly I want you to be aware of these double roots. And then what we don't see on the real number plane, we can then deduce how many imaginary zeros there's going to be. Now, I'm going to introduce a couple new theorems. One is the complex conjugate theorem, and it basically states that if a polynomial function with real coefficients and a plus bi is an imaginary zero of f, then a minus bi is also 0f. So in other words, if you have one complex function or complex number as a solution or 0, its conjugate must be 1 as well. And the irrational conjugates theorem down here states the same thing, except it's for irrational numbers. So if I have a plus the square root of b as a solution, a minus the square root of b must be a solution as well. So we want to be aware that this applies both to complex numbers as well as irrationals. So let's look at an example here where this would come into play. So this problem simply states we're going to write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1 and 2 and negative 2, minus 5i as 0. So we're going to have a leading coefficient 1. That's the only leading coefficient we'll deal with these particular problems. But we know we have two zeros here of 2 and negative 2 minus 5i. So a real number and a complex number. So when I set this up, so I'm trying to figure out, in other words, what is this function that has these roots? And I know that this function has, in fact, 3 roots, because I know that negative 2 minus 5i is a 0, and therefore its conjugate, negative 2 plus 5i, must be a 0 as well. So I'm going to set these up as factors. So with the 2 here, I know that since the 0 is 2, the factor must be x minus 2. And then we'll come up with factors that use this complex. So I have x, just like I have with the x minus 2, and this is going to be plus 2 minus 5i. And the reason why I know that this is plus is because this leads off as a negative. And so this is going to be 1, and I'm going to put separate parentheses kind of isolating this complex number. And since 2 minus 5i is going to be a complex, is going to be a 0 rather, then I know that x plus 2 plus 5i must be a factor as well. Now we need to write this in standard form. So let's do that. Now this will be a lot easier if I change my grouping here. So this is a little trick, if you will. We can change our grouping by using the associative property with those second factors. So I'm going to bring down my x minus 2 first. We'll mess with that a little bit later on. And instead of grouping the 2 minus 5i, since we can use the associative property here, since it's all addition. I know it says minus here, but remember, subtraction is simply the additive inverse, so we're saying plus and negative. So I'm going to change my grouping here as x plus 2, and then minus 5i, and then I'm going to group together the x plus 2 here. And I'll show you why I'm going to do that in just a moment. Okay, now if I look at this carefully, what I have basically a difference of squares, where I have one term, this is like a minus b, and over here this is a plus b. And we know that when we multiply those together, that should give us a squared minus b squared. It's we learned that a while ago, that difference of squares pattern. So we'll apply that here, because we could just you could multiply together using the distributive property, but it'll be a huge time saver if we just simply use this property. So I'm going to do a squared, so a being x plus 2, so x plus 2 squared, minus b squared, where b we have the 5 i's, and that's going to give me 25i squared. Okay, now let's simplify this. So still just bringing down the x minus 2, we'll mess with that at the end. And this is a special product, this x plus 2 squared. We know that as x plus 2 times x plus 2. And that special product simply says a squared plus 2ab plus b squared. Like so. And then I have minus 25i squared, and I squared is negative 1, so that becomes plus 25. Now I can I can really drop these inner parentheses and just add the 25 with the 4. So that will give us, so x minus 2. And then we're left with x squared plus 4x plus 29. Okay, now we can multiply this binomial with this trinomial using our distributive property. That's going to give us x cubed plus 4x squared plus 29x minus 2x squared minus 8x minus 58. So we're just distributing the x with each term and then distributing the 2 with each term. And now all we have to do is combine our like terms. So this will give us our final answer. So f of x is equal to x cubed. So we have 1x cubed, and then we have a couple x squareds. So plus 2x squared. And then we have a couple x's here. So plus 21x. And then finally minus 58. So minus 58. And that will be our polynomial given those specific zeros. And that's all that's to it. So that's applying the fundamental theorem of algebra, and I will see you on the flip side.